to today's webinar, Improving Crystallization and Precipitation, a review of 20 years of best practice. So we'll just go through the overview for the work that we're going to look at today. So we're going to first take a look back and kind of study how crystallization has gone from being an art to more of a science. Then we're going to look at a typical crystallization workflow, and from that workflow we're going to take a number of case studies from the literature and study how different techniques and tools have been used to improve crystallization and precipitation processes. Finally, we'll look at a quick reference list that's going to be available for anyone who gets in contact with us either through the chat box or sending us an email before we conclude the webinar today. So, why is crystallization important? Well, crystallization is used extensively as a means of purification, separation, or isolation of drug intermediates and API. Crystallization is very often the means of producing the solid form of an API as it is to be used in the final drug delivery vehicle. So for example, if you take a tablet, the API or the active ingredient in that tablet, the last step that it went through was typically probably a crystallization step. So the ability to consistently produce the desired solid form, so the desired crystal or precipitant, the desired solid form product has a very significant impact on the product quality and the process economics, in other words, the profitability of the manufacturer of this product. So what is crystallization? So crystallization, very simply, is when a solid is formed out of either a vapor, a liquid, or a gas. Typically, an industrial crystallization process involves the precipitation or the crystallization of a solid product from a liquid. So what we're looking at here is an image of some crystals in solution. And we can see in this case that they're very much like boulders, so they're kind of large boulder-like crystals that we're looking at. And the scale on this graph here is about 1600 microns across. So those crystals are probably 500–600 microns in diameter if you assume they're kind of spherical. Now crystals don't always look like this. Here's another example of a crystal, and we can see this one looks more like a flat hexagonal platelet. And we have a few more examples like this. So in this one we can see it's a bimodal distribution of crystals. We've got these large fuzzy agglomerates and surrounded by those agglomerates are what look like individual crystals as well that are much smaller in size. So in this case you've got the same crystal form in there, but it's a very different distribution of particles that you've got. You've got big ones and you've got small ones together at the same time. And finally you can see that you get some quite exotic crystal forms coming out. In this case what we're looking at is a dendrite, and what we see here is an initial seed crystal or a small crystal has grown out in many different directions to form something that looks more like a Christmas decoration. Now the key question here is, what impact will these different crystal forms that we can see clearly, what impact do they have on the process? Well, let's take filtration for example. So after a crystallization, it's important to be able to filter the material easily and efficiently. So if we look at our blocks in the top left hand corner, chances are they're going to filter pretty well. So the filtrate is going to go down in between the gaps left by those large crystals, and the filtration time should be pretty consistent and pretty quick. However, if we look at the other three, I think we're going to see some major differences. So the platelets, for example, what we see with the platelets typically is that they pack on top of each other on a filter, and they actually block the gaps for the filtrate to go through. So this actually makes the filtration times very long for a crystal that looks like this. In the case on the bottom left, where we've got our bimodal distribution of crystals, that's also the case. So what happens is you have these large crystals that go down into the filter bed, but then you also have these smaller crystals which tend to block the gaps left behind, and the filter time can be very slow. And in the case where you produce crystals that look like this dendrite, what tends to happen is when they go into the filter, they break. And when they break up into these very small and irregular pieces, once again you get the larger pieces which get blocked, or the holes left behind by the larger pieces get blocked by the smaller ones, and the filtration time again can be very long. So you can see how in this one very simple example to do with the shape of the crystals you produce, how that can impact the crystallization process as a whole and the downstream operating processes too. So in order to design and develop a crystallization that's efficient, you need to consider factors such as these. So, how do we actually generate crystals from solution? So typically the methods that we see in industry are cooling is probably the most common, followed by anti-solvent, and then there's also some evaporative techniques used, and then reactive crystallization is also seen quite a bit as well. So in a cooling crystallization, it looks something like this. This is our reactor. We cool down the contents, and crystals crash out. In the next example, anti-solvent, we add a different solvent to the solution, one that the crystalline product has a lower solubility in. You can see the volume increases, and we get crystals coming out in this case. Now we look at evaporation. With evaporation, we do essentially the opposite of cooling. We heat up the jacket. Our volume goes down as our solution evaporates, and what we're left behind with, or as the solvent evaporates, and what we're left behind with eventually after time is the crystals left in that kind of lower volume of solvent. And finally, we have a reactive crystallization. So it's very similar to anti-solvent, except that it's based on a chemical reaction. So we add our second, for example, an acid to a base. We add our acid to our base. You get a chemical reaction, and crystalline product crashes out in the form of a salt. So we're going to introduce a concept here called the Crystallization Treasure Map as a kind of bit of fun before we get into the real details. So what we're looking at here is a solubility and metastable zone width curve. So these are the building blocks for your crystallization. On the x-axis we have temperature, and on the y-axis we have our concentration in solution. So if you look at the solubility curve, the blue curve, you can see at higher temperatures we can get more of our product into solution. Now the metastable zone width is simply the point at which our crystals are going to crash out if we cool down. If you cool down from the point at the start that's marked there, the crystals aren't going to crash out at the solubility point. They're going to go into a metastable region and crash out at some point, and we call this the metastable zone width. Now if we imagine our crystallization, outside the metastable zone width, we have what we like to call filtration and impurity hell. So if your crystallization begins to operate in this region, you tend to get very fine particles. You may get phase separation. This can cause issues with filtration as well as impurity issues if these crystals agglomerate with that impurity of that oil present. So if you operate your crystallization like this, in an uncontrolled manner, where you don't know exactly what's going on, you can move into this filtration and purity hell before you get to your endpoint at 0 degrees in this case, when you get your full yield out. Now the other way to operate is in the black hole of dissolution, as it's called. And in this case, when you move along, you might move in and actually dissolve these crystals and then recrystallize them, and you never know exactly where in the process you're going to be, and this is typically equally as bad. It can impact your yields before you get to the end. So in order to be able to improve a crystallization process that might look like this, we need to have tools and techniques that are going to be able to tell us what our solubility curve is, what our metastable zone width is, where we're operating inside them, and then also what impact does our crystallization process have on the size of the crystals, the number of crystals, the shape of the crystals like we showed in the earlier example, and then other stuff like the purity and yield of the crystals too. So in order to get from a situation like that, where we had an uncontrolled process where we didn't know what was going on, a lot of research has been done. So initially, maybe 20, 30, 40 years ago, crystallization was considered an art rather than a science. But through the work of a lot of different people and the publication of a number of different articles and books, it's beginning to move, or it has moved more to a science than an art. And we have the science now to back up crystallization processes in order to design, develop, and scale them up well. So there's been a concerted research effort, and like I said, it's in the form of books. Here's 4 of the cornerstone books for crystallization research. We've got Myerson's Handbook of Industrial Crystallization. We've got Crystallization by Mullen, the Crystallization Technology Handbook by Mersman, and Crystallization Process Systems by Alan Jones. And these are great books for getting the basics of crystallization down, and they move on to more complex techniques as well. And these are a must for every library in a crystallization lab. There's also been a numerous number of papers published on the topic of crystallization. So a quick search on ACS, the ACS website, lists 1,300 papers on pharmaceutical crystallization. So that's just in one source, 1,300 papers on pharmaceutical crystallization. And that doesn't include all the other types of crystallization as well, from the chemical industry, for example. So there's a huge wealth of research out there on the topic of crystallization. The other source where a huge amount of work has been done is at conferences. So at AICHE, ACS itself, BIWIC in Europe, ISIC in Europe as well, our own process development conference, conferences like Scientific Update. There's been a huge number of contributors to conferences like this, and they're a great source where people can come together and meet up and discuss the work that they're doing. So it's through the books, papers and conferences that we really have moved from a case where it was crystallization was more like an art, and we're moving towards the case where it's like a science. So over the past 20 years as well, in conjunction with this kind of research effort, MT or Mettler-Toledo tools have also been used to drive this improvement. So for example, the most commonly used techniques in crystallization are without a doubt LaserTech and PVM for in situ monitoring of the crystallization process. And they're used at every pharma company to design, develop, scale up and optimize crystallization processes. So here we have LaserTech in the lab, which can operate down to like a 5 mil scale. We have PVM, which is an in situ video microscope, which gives an instant understanding of what's going on in a crystallization process. We'll have some examples of this later on. And then finally LaserTech in the pilot plant or in production, where you can actually monitor your full-scale crystallization process. There's also React-IOR, another Mettler-Toledo tool, and this is used to monitor supersaturation, the driving force for crystallization, and it can also be used to actually control a crystallization process, and we have a nice example of that a little bit later on. So here we have React-IOR in the lab and React-IOR in the plant. So again, they cross both scales. Another piece of the puzzle is the automated lab reactor. So we have the RC1, the LabMax, and the Multimax. And these are used to precisely control important crystallization parameters, facilitate the scale-up and scale-down studies. So for example, the impact of mixing on a crystallization process is always very important, and to be able to control your mixing precisely is vital to be able to do scale-up, scale-down studies. All of these reactors can also be automated, so it's possible to leave them running overnight and do kind of some of the more laborious work for you. So here we have a Multimax with our 2 LaserTech probes in it running in parallel. And then we have a LabMax, which is a larger system, running with a React-IOR to measure supersaturation. So with this in mind, we go back to our treasure map. So in this case, we have our filtration and impurity hell, and our black hole of dissolution. And where this might have been the case a number of years ago, I have tools that can actually really characterize this fully and see exactly where you are in the process. So in this paper from the International Journal of Pharmaceutics, I have the reference down at the bottom. We can see the solubility curve there, and we can see what our crystallization looks like, physically measure it. We can see what it looks like in terms of our cooling rates. So at 4 different cooling rates, you can see that you get a very different level of supersaturation, or a different path towards your endpoint in each case. And this is going to impact the quality of the product that you get out. So to be able to see this and measure this is extremely important in order to design and develop these crystallization processes. So another example from University College Dublin, which kind of goes through all the techniques. So this is done in an automated lab reactor. You can see, again, you have your solubility curve. The solubility curve in this case is reversed because it's an anti-solvent crystallization. So what we're doing here is adding anti-solvent to a saturated solution, and it's crashing out. So you can see it moves inside the solubility curve, and we have 2 different rates. So we have a 0.2 gram per second addition rate and a 0.1 gram per second addition rate. So you can see, depending on the addition rate you use, the path towards the end of the crystallization is very different. And we can translate that to supersaturation. So just by, we know our solubility curve, we know our concentration, we can figure out the supersaturation. You can see that when we add fast at 0.2 grams per second, the supersaturation is higher throughout the crystallization process. So it's great to be able to know that, to see what impact our process parameters have, but what impact does that have on the product itself? So this is where the LaserTech comes in. So you can see when we add fast in this distribution, we have more fine material, and there's far less coarse material when we add fast. So in order to control our particle size, it's very important to be able to control the supersaturation, and to do this we control our addition rate. A slow addition rate in this case leads to much bigger material and less fines. And then finally we can back this up using the PVM. So now we can see the PVM, we can get an idea for the morphology of the crystals, the size of the crystals. It may give us an indicator as to how these are going to flow, or how they're going to formulate, or how they're going to filter downstream. So this is the case where we added our anti-solvent slowly. And here's the case when we add it fast. So when we see we add it fast, we definitely have an agglomeration problem. So looking at this image, it's important to see that maybe there's going to be impurities trapped in between those crystals. This may not filter well because they're going to break in the filter and clog the filter up. And they may not also flow too well as well. And the benefit of using the PVM in this case is that you don't have to sample. If we were to sample the second example here with those agglomerates, there's a very good possibility that they break up and you just see individual small crystals, which is not an indicator of what you actually have in your process. So, having just given a little background into how the idea behind moving from the crystallization art to more of a science, we'll look at a typical crystallization. So this is typically how it might work. So the initial idea when you get any new crystallization is you want to try and understand the crystallization process. You then move towards characterization, and then eventually up to scale up, and finally on to full scale production if the API makes it that far. And the scales that you work at typically tend to be very different depending on what you're doing. So when you're trying to understand and characterize, you might be working in the laboratory between 5 ml up to 5 liters, for example. This is just a kind of ballpark estimate. It depends on the company, it depends on the goal of the project, but an estimate of the kind of scales people typically work at. So the laboratory from 5 ml up to 5 liters, the pilot plant from 5 liters maybe up to 100 liters, and then in production above 500 liters all the way up to these huge crystallization vessels producing tons and tons of material a day. So what are the steps involved in this crystallization workflow? Well, initially, like I said before, you want to characterize the solubility and metastable zone width. These are the building blocks for your crystallization process. The next step might be to understand supersaturation. You then might want to look at seeding, what impact seeding might have. Seeding is a very good way of controlling the final particle size. Then as we move towards the characterization step, you might want to think about scaling up. So maybe you want to look at pushing the limits of the crystallization, like cooling very fast or changing the agitation intensity. And in this case, you may get something like oiling out appearing, and that's something you want to be able to try and avoid. You may observe polymorphic behavior. Typically this is the case for complex organic molecules, is that they'll have more than one polymorphic form, and to be able to control the polymorph to produce the right one is very important. As we move further along, you may want to start thinking about how this material is going to formulate. So downstream, you've got after the crystallization step, you're going to have to filter, dry, you may have to mill, then it's going to go to a granulation. It might be a high shear granulation, followed by another drying step, followed by a flow into a tablet press. So all that formulation, all those formulation processes are going to be impacted on what size distribution or shape distribution of the API that you have. So in order to design a process that's going to formulate well, you have to think about what you're designing in your crystallization vessel itself. As you scale up, you might want to think about the impact of mixing. And then finally, as you go to production, impurities may become an issue, of course, impurities are going to be an issue at the start, but the example that we're going to show is kind of more of a production-orientated example. And then finally, an example might be you want to optimize your production process, optimize your filtration rates by producing crystals of the size which are most suitable to a fast and consistent filtration time. So in all these examples, and there's a lot more besides, there's a wealth of information in the literature covering all these issues and how our tools have been used to improve the crystallization surrounding these steps. So the first example we're going to look at, we'll start at the start and we'll move through. We're not going to look at every example because time won't allow, but I will give people the references to these if they'd like. So we'll start with the solubility and supersaturation. The paper that we're going to look at is by Barrett and Glennon. Characterizing the metastable zone width and solubility curve using Lasentech, FBRM, and PVM. So this is the seminal work where Lasentech was first used to characterize the metastable zone width and solubility curve. And it's a great paper for anyone interested in measuring these key parameters and how to do it in the most efficient way and what gives you the most relevant and accurate data. So, like I said, so the example is characterizing the metastable zone width and solubility curve using LazenTech and PVM. So LazenTech was used to generate the solubility and metastable zone width curves for a cooling crystallization. And this is how they do it. This is the kind of the simple graph that shows exactly how it's done. So the idea is that you want to identify the temperature at which crystals nucleate, which is a point on the metastable zone, and the temperature at which they dissolve, which is a point on the solubility curve. So in this graph, what we're looking at here is there's three different trends. The first is temperature. So you can see it's a simple cycle where we cool down to a point, and at 60 minutes we start to heat back up again. So it's a cooling step followed by a heating step. And the other two trends that we see are LazenTech trends. So this is data we get from the LazenTech. And we can see initially we have a saturated solution. So the LazenTech for the first 40-50 minutes is reading 0. Essentially there's no material present in solution. There's no particles that the LazenTech is picking up. At a certain point you can see it begins to rapidly increase. So the fines increase rapidly. The coarse also increase as well. So at this point, this is the point of nucleation. And you can measure this very accurately, figure out what temperature it is, and there you have a point on your metastable zone width. Now, as soon as this happens, the heating step was initiated, and then during the heating you can see that the crystals began to dissolve over time. And then you can essentially the point at where they dissolve and where they go back to that flat line again, that is the point of dissolution, and that's a point on your solubility curve. So LazenTech accurately detected the point of nucleation, a point in the metastable zone width, and the point of dissolution, which is a point on the solubility curve. And by measuring these points at different concentrations, the solubility curve and metastable zone width were rapidly generated. So before we look at the solubility curve and metastable zone width that they generated, there's one important point to make here, and it's the statistics that you should use when you're trying to identify the point of nucleation and the point of dissolution. So when you initially nucleate material, it tends to be very small. So when you want to identify really accurately the point of nucleation, you should look at the fine counts. For example, a statistic between, in this case they used between 0 and 20 microns. And what they saw was that the trend between 0 and 20 microns began to increase earlier than the trend for the larger material. And that makes sense because initially in the nucleation phase, it's small material that's crashing out. Now, if you want to accurately measure the point of dissolution, you should use the coarse counts. So what they saw was actually the fine counts here between 0 and 20 microns disappeared first, and then it was the larger counts that disappeared after. And this also makes sense because small crystals tend to dissolve faster than the large ones because they have the higher surface area to volume ratio. So whenever you're trying to accurately detect the point of dissolution, look at the coarse counts because they're the ones that are going to dissolve later, hence making a more accurate measurement. So now we look at the solubility curve that they generated. So you can see here what they did was they measured the solubility curve and then also measured the metastable zone width critically at two different cooling rates. So the metastable zone width, unlike the solubility curve, is not a fixed point. It will change depending on the process parameters that you choose. So this is a very important point when you think about scale up. So you can see here that there is a significant impact of the cooling rate on the point at which these crystals crash out at every concentration. So if you scale up from a small laboratory scale to a large production vessel, the cooling capacity at the production scale might be very different to what you get at the lab scale. It also may be more variable than you get at the lab scale. So this can be very important when considering the impact that a scale-up has on the crystallization process, is that its capacity to cool may impact the metastable zone width, which impacts the point of nucleation, which impacts the whole crystallization. So it's very important to characterize this at the small scale and to be able to mitigate against it as you scale up. So, summary and conclusions. So there was a second part to this study, and it involved the PVM. It was actually done in kind of tandem. So the first thing is the LazenTech can be used to rapidly generate the solubility and metastable zone width information. But the PVM was also used in this case to see what the crystals looked like as they nucleated and as they dissolved. And some of the data that's shown was pretty interesting. So you can see this snapshot or image taken from the PVM. This is again is the in-process video microscope, shows the crystals, and you can see they're quite pointed. There's some agglomerates there perhaps, but the key thing here is the pointedness or the sharpness of those crystals, and that's taken within 2 minutes of the point of nucleation. Now if we look during the dissolution process, you can see that the crystals are much more round in shape. And again, this makes sense. It's because those edges or points on the crystal are the first points to dissolve, because their surface area to volume ratio is higher and they tend to dissolve much quicker. Now this has important implications when you consider efforts to try and change the shape of your crystals for one reason or another. So what is implied here is that temperature cycling may be used to impact the size and morphology of your crystals. If you were to heat your crystals followed by a cool followed by a heat, you have the possibility of changing the shape of your crystals, and this can be very important for downstream processes such as filtration. If you look at the top picture, this may not filter so well, but if you've got nice round boulders like the one on the bottom, maybe it's going to filter a lot better. Also, in the case of flowability, potentially, depending on the shape of the crystals, the flow might be a lot better in one case or the other. So changing the temperature and doing a temperature cycle can impact the morphology and the shape of the crystals, and this can be important. So back to our crystallization workflow. So the next example we're going to look at, because it's a really critical one, is supersaturation. The example we're going to look at is from Vince Liotta and Vijay Subhasu. This work was done at Shearing Plough, monitoring and feedback control of supersaturation using ATR FTIR to produce an active pharmaceutical ingredient of a desired particle size. So this is the case where they wanted to target a particle size, and they used a control loop to control the supersaturation in order to do this. And this is the first paper that employed this technique that was published, and it uses React-IR and LaserTech together. So before we get into it, let's just see why supersaturation is important. So the two main driving forces for crystallization are crystal nucleation and crystal growth. So we can see the top one here, crystal nucleation. It looks something like this. It's simply the birth of new crystals. And there's a simple equation which relates B, which is the nucleation rate, in other words, the rate of change of the number of crystals with respect to time, or the birth of new crystals with respect to time. It equals some constant multiplied by the supersaturation, delta C, raised to some power. Now in the case of crystal growth, we can see it looks like this. It's simply the increase in size of the crystals. So G, the growth rate, is the rate of change of one length, specific length of the crystal with respect to time, and that equals some constant multiplied once again by the supersaturation raised to some power. So in both cases, supersaturation is the driving force for crystallization and crystal growth. Now by controlling supersaturation, nucleation and growth can be controlled, and this allows the crystal size to be controlled as well. So if you want to target a specific crystal size, it's absolutely paramount to control the supersaturation. And that's exactly what the goal of this paper by the guys at Shearing Plough was. So the idea was to use React-IR to directly monitor and control supersaturation during a seeded crystallization experiment. And then secondly, they wanted to use LaserTech to confirm the kinetics, i.e. the region of growth or nucleation. So controlling the supersaturation is great. It gives you a consistent crystallization, but you also need the other side of the story. You need to look at the solid side as well, and seeing what impact that flat and straight supersaturation level has on the kinetics of the process. So is it growth dominated? Is it nucleation dominated? Is it a mixture of both? So here's a little schematic of the setup that they used. They've got their crystallizer in the middle with the LaserTech and React-IR probes inserted. It's all hooked up to a temperature controller via a control system. And the idea was to set the supersaturation set point at a given level, and using the control system they wanted to control the temperature, in other words reduce the temperature so as to keep the supersaturation at the set point. And this is the result that they got. So you can see the set point here in this case was set at 1.5, and you can see initially the supersaturation drops to that level, and it's maintained pretty constant over that level over a 12 or 14 hour period. Now the cooling rate that allowed them to do this, or that the controller gave in order to keep the supersaturation at this level is very non-linear. So you can see on the grey line here, this is the temperature. So you can see initially it's pretty flat, and then it begins to reduce slowly, and then eventually they get to a point where it kind of falls off a cliff and they cool very rapidly towards the end of the batch. Now the reason the curve comes out like this is because at the start of the batch the surface area is very low. So the surface area available for growth is very low. So in order to keep the supersaturation constant, they want to be able to grow these crystals slowly. They've got to cool very slowly at the start. Now as the surface area increases, they're able to cool more quickly because they can use more of that supersaturation to grow on that larger surface area. So the generated cooling profile from the control algorithm was found to be non-linear. Now the next thing that they did in tandem with that, so the React IOR and the Lasentech were both in the crystallizer. Key Lasentech stats were tracked with the crystallization kinetics. And here we can see what they look like. So the dark line represents the fines, so between 1 and 50 microns. And you can see they reduce pretty rapidly over time. And that makes sense if your crystals are growing. So if you add small seeds, they grow into larger size ranges, so the number of crystals in that smaller size range is going to decrease over time. The second statistic is the gray statistic, and that's the square weighted median. And in this case they use the square weighted median to track crystal growth. And you can see that increases pretty linearly and consistently over time, indicating that they're getting a very nice growth rate when they keep that supersaturation level constant. Now obviously they go into a lot more detail about the setup of the controller and everything in the paper, and it goes into a lot more in-depth data analysis. So I'd suggest if people are interested in this paper and how to do it, I've listed the references at the bottom of each of these slides. So summary and conclusion. So by changing the supersaturation level, essentially they did two experiments. They did one experiment at 1.5 was the supersaturation set point, which is the example I showed. And the second example was where they set the supersaturation at 2, so a higher level. So one was a high supersaturation and one was a lower supersaturation. And depending on where they set the set point and control the supersaturation, they got a different answer with the Lasentech. They got different kinetics, and under the microscope, like we see here, they got different crystals. So this is when the supersaturation was set at 2. So you can see these are about 100-150 microns long, probably about 30-40 microns wide, and you can see there's some small crystals in there as well. Now when they set the supersaturation lower, you can see these are kind of fatter, longer crystals, and there aren't as many as those small crystals in there as well. So you can directly see the impact that changing the level or controlling the supersaturation at a different level had on the crystallization. So a lower supersaturation level results in larger crystals. And the cubic cooling profile in each case was generated, indicating that these are the preferred profiles for optimal cooling crystallizations. And that makes sense based on the surface area argument made earlier. So back to our workflow. The next thing that we're going to look at is oiling out. So this one has a kind of long title. It was work done, I think, at DuPont. Via BMS, and it was process development challenges to accommodate a late appearing stable polymorph, a case study on the polymorphism and crystallization of a fast-track drug development compound. It was a fast-track development compound, and a new polymorph, a more stable polymorph, appeared during the process. So here in the top right we can see our X-ray powder diffraction patterns. During the drying process, this is when it appeared. So we can see form 3, form 1, and then a mixture of the two that appeared. So what they did was they chose a new solvent system to accommodate this form, but when they used it, it resulted in a solvate formation. So they needed to figure out how to remove this solvate issue. So they used PVM, so they used the in-process video microscope to rapidly characterize the solvate crystallization mechanism. And what they discovered was the formation of a quasi-emulsion. And this is what the image looks like here. So again, if you want to go into more detail about the background to this story and some of the more in-depth analysis, I have the reference here at the bottom. But what we can see here is that the PVM clearly shows they're not crystals. This is like as coined by these guys, a quasi-emulsion was formed during the crystallization process. Now obviously this would be something very difficult to see in the crystallizer, and if you sampled this and looked at it on the microscope, you probably wouldn't be able to see anything either. So the PVM gives you great ability to rapidly characterize and immediately understand exactly what's going on in your process, and an image is an image. This is very easy to interpret. There's no trends associated with it. So in order to accommodate this unusual or this process upset, the solid-liquid phase boundaries were characterized fully in order to identify suitable areas of operation. And this is a very nice study. So you can see the phase diagram that they generated here, the areas in which the emulsion formed when they had liquid, solid. And they had 3 different protocols that were tried or used in order to avoid this quasi-emulsion formation. But the only way really around it was to implement a reverse addition process. So if you look at the top of that graph or phase diagram, you can see protocol 3, the arrow coming in from the top, indicating it's a reverse addition. So they can get to their endpoint without going near this quasi-emulsion region where this will be formed. So a reverse addition crystallization protocol was chosen, and this was chosen to ensure that the stable form was there throughout. And then once again, PVM was still implemented in the crystallizer, and some agglomerate formation was identified. So you can see here that the crystals are forming these large agglomerates. You can see the individual crystals around them, but ultimately they're forming these agglomerates. And they were able to control this issue using by changing the agitation intensity. So once they had chosen this reverse addition to ensure that they got the stable form, there was still another problem that they had to deal with, this agglomerate formation, which was going to impact their downstream operations. But changing the agitation intensity really helped with this. So like I said, the reference is down there on the bottom. It's a really nice paper to look at and to go into a lot more detail. We're really focusing on the aspects of the PVM here and how they actually redesign the process, but there's a lot more to the study than that, and I'd suggest people read it. So once again, back to the workflow. So like I said, we don't have time today to go through all these examples, but there are papers out there on every single one of these steps that I mentioned, and a lot more besides. So there's a great paper on an antimeric resolution. There's different papers on a ton of different things. And if people, again, just submit into the chat box that they'd like the reference list, we'd be happy to provide it, or else just send an email. So the next one that we're going to look at, this is the second last one, we'll do one more after this, is to ensure formulability. So the work was done at BMS by Kim et al. So it's the control of particle properties of a drug substance by crystallization engineering and the effect on drug product formulation. So like I said earlier, the crystallizer, once you produce that API, depending on the quality of the product, its size, its shape, etc., it's really going to impact on the formulability, the downstream formulability at the next step. So this is a study into this kind of thing. So there was 2 parts to this study. The first part of the study was to produce optimal crystal properties to facilitate filtration for a start, drying, and then powder handling. So to do this, the process was redesigned. So the initial process looked something like this, and this is taken from the paper. So they added sulfuric acid, then they added the seeds, and then they added heptanes to crash out the material. So this was a very uncontrolled process, and it wasn't producing the desired crystal product. So the process was redesigned to look something like this. They added the seeds first, and this provides the surface area for growth, and you can control firstly the point of nucleation when you add the seeds, but then also it provides surface area for further growth. It helps control the process. And then the sulfuric acid was added at a specific rate, or in this case at different rates depending on the experiment over time. And they use laser tech to characterize the impact of addition profile and seed loading on the crystal size. And these are the results that they got. So what we have here is 3 laser tech distributions taken at the endpoint of a crystallization. So in distribution A, in this case, was a linear addition profile with 0.5 weight % seeding. So like I said earlier, a linear addition is sometimes not the best way to add your anti-solvent or your acid to your crystallizer. It sometimes pays off to add in a non-linear fashion, so slowly at first, and then you can ramp up the addition rate at the end. And this is exactly the case here, because a linear addition profile has produced the most fine material, around 10 microns there. Distribution B is the cubic addition protocol, and in this case again they use 0.5 weight % seeding, and they can see just by using a cubic addition profile, you can see they produce less fines and a larger crystal at the end of the batch. And then the best of all, in these terms, in terms of producing the largest particle size or crystal size with the smallest or lowest number of fines, was to use a cubic addition protocol with 5 weight % seeding. So by increasing the mass of seed at the start, I think basically this just increases the surface area available for growth, and you get more growth as opposed to nucleation. So you end up with a larger crystal at the end and less fines. So part 2 of this study was to design the drying process to ensure a consistent formulation and a consistent drug performance. So not only do you have to go through the formulation steps like your drying, your granulation, your milling for example, it then has to be tableted, and then it has to go through dissolution testing or QC analysis in order to ensure that the tablets are meant to do what they do, or do it in the best way possible. So Lasentech was used to study the impact of dryer parameters on the crystal size. So Lasentech isn't only used for crystallization, it's kind of what we're focusing on here today. It's also used extensively in formulation processes in applications like high shear wet granulation, fluid bed granulation, fluid bed drying, in spray coating, in dissolution, in roller compaction. Anywhere you can insert the probe into a process where there's particles, Lasentech typically provides a lot of value, and this is a very simple example of that. So what they looked at was 4 different types of dryer: a tray dryer, a filter dryer, a conical dryer, and a tumble dryer. And you can see that the crystals, or sorry, the particles produced at the end of each drying step was very different. So some were more fine, some were larger, some were intermediate. So you can clearly see the impact of the type of dryer used and how that impacts on the particle size at the end of the batch. And this is critical, so depending on the dryer that they use, this might go on to the next step where it's tableted, or it might go through a granulation step. And if there's inconsistencies, or if there's too many fine particles, it's going to impact those downstream processes and have an impact on the product quality at the end. So a process resulting in a suitable dissolution profile was generated. So here we look at the dissolution profile. Here we're measuring the percentage of API dissolved. So you can see curve A is very good. You can see you get almost 100% after about 10 minutes, which is what you're after. You want that API to be in solution very quick, because that shows that it will act very fast in the body. Curve B is not so good. So this was from the filter dryer with normal agitation. And then C is the worst of all. So C is the API subjected to the high shear milling. So probably in this case, due to the impact of the high shear milling, you got a different particle size, and that impacted the tableting properties, so that this actually dissolved in a different manner. So everything traces back along the way. Your dissolution test here depends on your parameters in your dryer, and the parameters in the dryer depend on the type of dryer that you use, and also the raw materials that come in from your crystallizer. So ultimately, the key is to control your particle size at every step along the process in order to produce the product of the highest quality, which in this case will be product, or in this case will be product A here, where it dissolves extremely quickly. So the final example we're going to look at is the impact of impurities, and this is from AstraZeneca. So we're Claire Scott and Simon Black's work, inline analysis of impurity effects in crystallization. So in this study, like I said, it's from AstraZeneca. Here we just have a quick, the diagrams of the 2 molecules involve the impurity in the compound. So Lasentech was used to study the impact of impurities on crystallization kinetics. So this is the data that they got. So a pure crystallization versus an impure crystallization. How long does it take to reach its endpoint? So with the pure crystallization, you can see the crystallization was very rapid and it plateaued pretty quick. When impurities were present, you can see that the crystallization took a lot longer. So you can see it's still increasing, the counts per second are increasing over time, indicating that the crystallization has not reached an endpoint. And you can see also here with these micrograph images that depending on whether the impurity or not is present, you can see you can get a very different morphology of crystals. You get nice long needles in the case where there's no impurity, but when there's impurities present, you can see it really inhibits the growth. It inhibits the growth and you get a very different morphology. So the Lasentech monitors the relative growth and nucleation rates at different impurity levels. In-process monitoring ensures that varying impurity levels will not impact cycle times and yield. So in the case where you may have varying impurity levels coming into your crystallizer in the plant, if you just have a set endpoint, if there's impurities there, you may actually lose yield because you're not running the crystallizer for long enough. Whereas if for some reason you get very pure stuff coming in, you could actually reduce the cycle time. You could end your crystallization a lot quicker because it's complete a lot sooner. So having the Lasentech in the plant to be able to call an endpoint to your batch can be very useful for ensuring you maximize yield as well as ensuring that you optimize your cycle times. And then, just a quick aside here, that the PVM can be used to determine this in process without the need to sample and to use the micrographs here. So once again, the references down the bottom is Scott & Black from Organic Process Research and Development. And this is a very nice, simple paper outlining how this study was done. So quickly, we're going to go to the references. Firstly, I'd like to acknowledge the Mettler-Toledo crystallization team, my colleagues Paul Barrett, Terry Redman, Jorg Werlicek, Brian O'Sullivan and Jochen Scholl for their help putting this presentation together and reviewing the tons of literature that really is out there. These are some references from academia on how our tools have been used to improve crystallization and precipitation. I know people aren't going to have time to jot all these down, so please just enter in the chat box if you'd like a copy of this reference list. This is actually incomplete. There's a lot more to it than this. Please just enter in the chat box or email us and we'll be happy to send it on. And here we have some references from industry once again. Some of these I've shown, but there's plenty others out there on all the examples I showed, and a lot more besides. And once again, we'd be happy to send these on. So just to conclude briefly, so improvements in technology have gone hand in hand with improvements in understanding and design of batch crystallization. This has provided the ability to confirm and enhance the creativity of the crystallization artists who were operating years ago, and it does this because you can better control and observe directly what is really going on in your crystallization process. And if you can really understand what's going on, it's much easier to improve the crystallization process as a whole. And finally, the next step is to look to the future, to try and anticipate the challenges that lie ahead and create the techniques and technology that will be able to meet these demands. So that's the end of the webinar. Thank you very much.